Today, we're going to continue talking about transient analysis of first order circuits. And we are going to really cover two different things today. The first thing that we're going to cover is the concept of time constants, which is going to ever so slightly change our equations. And then we are going to cover the concept of total response. All right, so as a very brief recap, what we did in class on Wednesday, because today is Friday, right? I know what day of the week it is. I'm an adult. We were looking at circuits that could generally be classified as follows. We had some equivalent resistance REQ connected to some equivalent inductance LEQ, like so. Let's define IL of t here. Just for the sake of argument, let's call this IR of t. Let's call this voltage VL of t. And we found that in general, Y of t, where this variable Y is taking the place of literally any current or voltage in the system, would wind up being of the form Y at 0 minus for t less than 0 minus, and Y at 0 plus e to the negative REQ over LEQ times time for t greater than or equal to 0 plus. That was the first thing that we did. Then we took a look at circuits containing capacitors, where we broke things down as a single equivalent capacitance. We were dealing with systems that could be described as follows, where we have some REQ, some CEQ, here's IR, here's IC, here is our voltage VC, and for these systems, we found that Y of t was equal to Y at 0 minus for t less than 0 minus, and Y at 0 plus e to the negative t divided by REQ CEQ for t greater than or equal to 0 plus. Is that a fair recap of what we learned in class on Wednesday? Okay. So, what's the difference between these two equations? The thing that is being multiplied by t in the exponential function. Absolutely right. Other than that, these equations are literally identical. So it really doesn't matter whether we have a first order circuit containing a resistance and an inductance, or a first order circuit containing a resistance and a capacitance. They behave in exactly the same way. It's just a slight variance in how their rate of exponential decay is classified. So in electrical engineering, we actually treat these circuits as if they're literally the same thing, and we put these in terms of what is called a time constant for the system. And so that time constant is just a measure of the rate of decay And we evaluate it one way if it's an RL circuit, and a slightly different way if it's an RC circuit, and then everything else is literally the exact same thing. Okay. So let's see what's going on in chat here. Isaiah, my screen is shared, so I don't know why you are unable to see things. Yeah. And for what it's worth, no one else in the Zoom chat is saying anything. That might mean they did see stuff. That also might mean they're not paying a lick of attention. There's no way for me to know. The people that are on Zoom in the classroom can see my screen. All right, so Emily can see as well. All right. So let's define our time constant, okay? So a time constant which we give the symbol tau to is the amount of time needed for a voltage or current waveform to decay to e to the minus 1, which is approximately 36.7%, if memory serves me correctly, and we'll figure that out in a moment, of its initial value. So mathematically, what this means is literally e to the t over tau must be equal to e to the minus 1. Or excuse me, e to the negative t over tau must be equal to e to the minus 1. And from this, we can see that the time constant for an RL circuit is literally just the equivalent inductance over the equivalent resistance. And the time constant for an RC circuit is just the equivalent resistance times the equivalent capacitance. So I'm going to draw a graph here. Here is our signal as a function of time. Here is time, and let's say that this value corresponds to y at 0 plus. I'm going to draw a table over here as well. And so this will be y of t divided by y at 0 plus. And on the left-hand side, we're going to have t. All right, so at one time constant, we're looking for y of t divided by y at 0 plus to be equal to e to the minus 1, which according to my calculator is 0.36787. So let's call that 36.788%. So roughly speaking, this would be one time constant, right? At a value of 2 tau, that ratio would be equal to e to the minus 2. Which is 13.533%. The value of tau doesn't change, so it's just 1 tau shifted over to the right. At 3 tau, we would be at e to the minus 3. Or 4.979%. At 4 tau, our ratio would look like e to the minus 4. Or 1.831%. And our last data point on the table will be at 5 tau, where our ratio would be e to the minus 5. And that is 0.674%. So the reason why I'm bringing this up is we can see that it takes approximately 5 time constants for the value of our voltage or current to decay down to less than 1% of its original value, which means it takes approximately 5 time constants for a capacitor or an inductor to fully discharge all stored energy. So earlier, or actually, I say earlier, on Wednesday, when we were talking about infinity being a point of time, what we're really talking about is 5 time constants. As long as we allow enough time to elapse so that our capacitor or inductor is fully discharged, that's the same thing as infinity to an electrical engineer's. So for all intents and purposes, we're really just looking at the circuit at least 5 time constants later and assuming we're at DC steady state, because we know that our energy storage element has lost practically all of its energy at this point. So this is what time constants are used for. It lets us have a figure of merit for saying how long we need to let the circuit charge or discharge before we do something else to it if we want to have nice, smooth looking things. And when we do our lab on Monday, you'll literally see what happens to your waveforms if you're operating your circuit at a frequency such that you're not allowing 5 time constants to occur. And you'll get these weird, funky looking shapes because you're not allowing your capacitor and inductors to fully charge and discharge during our cycle. Okay. So just trying to provide a little bit of context as to what t equals to infinity actually means in the context of transient analysis here. Okay. So it should be fairly obvious that now that we have defined what a time constant is, and I've given you the equations for what time constants are for an RL circuit and an RC circuit, we can actually just have one generic equation that works for both types of systems, right? And that would be simply y at 0 minus for t less than 0 minus, and then y at 0 plus e to the negative t divided by tau for t greater than or equal to 0 plus. And our fourth step would change to just say, find the time constant of the circuit during the transient condition, as opposed to find LEQ and REQ or find CEQ and REQ, because that all means literally the exact same thing, okay? So this is the generic equation that I'm going to be working with from here on out because it is the most general case and is applicable for all first order circuits. All right. So I'm going to scroll back up here before we start talking about our next topic. And I want to look at these circuit diagrams. Now, these are general circuit diagrams describing what was going on during our last class meeting. What can we say about what's happening to the sources as the switch changes states for these circuits? Exactly right. That's all that's happening for all of the problems we've worked to this point. Whatever type of source we had has been disconnected from influencing the behavior of our energy storage element during our transient condition, okay? That is what's called the natural response of the circuit, okay? Because it's what it does when we don't force it to do anything else. Today, we're going to be talking about the total response of the circuit, and that is effectively the opposite situation. How are these things going to behave if we add sources in, or if we make some change that results in sources being left in the circuit? Because it's the same thing. Okay. So the total response, let me just go to the next page here. There we go. So the total response of a circuit, which I'm just going to call a Y total, is the natural response, which is what we've been dealing with to this point, plus the forced response of the circuit. So the forced response of a circuit is how a circuit behaves when there is a forcing function, okay? So let's look at that simple RC circuit from the opposite perspective. Now, our switch is going to be closing at t is equal to 0. We have our R. We have our C. And here is our voltage, VC of t, okay? So what would VC at 0 minus for this circuit be? 0, because the voltage source isn't connected to the capacitor, which means the capacitor can't have any voltage or any stored energy. All right, so 0 volts. What would VC at 0 plus be? 0 volts, because the voltage drop across the capacitor cannot change abruptly. So whatever voltage it had at t is equal to 0 minus, it must continue to have at t is equal to 0 plus. Right? Now, what would be the value of the capacitor voltage at t is equal to infinity? Realistically here, just a long time after the switch is closed. So after the transient has died out, we're expecting a DC steady state response here, which means we should be able to just get a number. And because I didn't give you a number, I'm not really expecting an actual number, but I think Walker already said it. What was it? Yes, absolutely right. This part right here is literally just the forced response. It is the value of the capacitor voltage that this circuit is forced to have because there's a source left in the circuit. So the forced response right here is literally just whatever y is at t is equal to infinity. So if we were to modify our generic equation, and I'm telling you right now, there is going to be a slight error in this that we're going to have to fix, so maybe don't write everything down just yet. We would have y at 0 minus for t less than 0 minus, y at 0 plus, e to the negative t divided by tau, plus y at infinity for t greater than or equal to 0 plus. Now, there's an error here, okay? So if this were a capacitor voltage, this would look like Vc of t is Vc at 0 minus for t less than 0 minus, and Vc at 0 plus e to the negative t divided by Rc plus Vc at infinity for t greater than or equal to 0 plus. But what happens if we substitute our numbers in for this thing, right? So Vc at 0 minus was 0. Vc at 0 plus was 0. E to the whatever doesn't really matter because Vc at 0 plus was 0. And then we're going to have plus Vs here. What's the problem with this? It's no longer a continuous function. So we need to make a very slight modification to our general equation in order to take into account that our forced response, Vc at infinity, is being applied over all points in time, and it's not really just what this circuit is settling to as time progresses. So to fix that, instead of just having our initial condition here, we're going to have y at 0 plus minus y at infinity, and that will fix that discontinuity. Okay. So this is our generic equation whenever sources are left into the circuit. Now, one of the most common questions I get about this material is, how can I tell the difference between whether I have a natural response problem and a total response problem? And the short answer is, if there are any sources left connected to your capacitor or inductor, you have a total response problem. That being said, you can apply the total response equation and the total response analysis to a natural response question, and you're still going to get the right answer, because in a natural response system, your forced response is just 0, because you know that all of your signals decay down to 0 because there's no sources left in. So realistically, you'll spend an extra 20 to 30 seconds analyzing the circuit at infinity and being like, oh, nothing's happening. The answer was 0. That's the only difference if you choose to just use this method for literally everything. It will save you a little bit of time if you can recognize the difference, but it's not enough to stress out about, in my opinion. Yes, sir. So let's pull up some problems here, and maybe this will help illustrate things. So I'm going to look at web work. We're just going to use this to literally look at problems. Maybe I'll work one. We'll see. So this would be homework set, probably number 14 we should be looking at. All right. So for this particular problem, I would argue that this is going to be a total response problem, because even though the switch is doing something, that 2 amp source on the left is always connected, right? So regardless of whether that switch is opening or closing, the 2 amp source is always going to influence the behavior of the inductor on the right-hand side of the circuit. So this is a total response problem. A similar thing here, right? We have that 100-volt source on the left that is going to be connected or influence the behavior of the inductor on the right, regardless of whether or not that switch in the middle path is open or closed, right? So we still have a source in the circuit that is influencing the behavior of the inductor at t is equal to infinity, regardless of what position the switch is in. This is also a total response problem. Looking at you guys' last web work assignment, so this would be web work assignment number 13. If we look at this particular circuit, we can see that when that switch opens up, we're effectively breaking this circuit into 2 closed loops. And so the 2 amp source never influences the behavior of the inductor after that switch is opened up. So that's why this is a natural response problem. Looking here, the voltage source is very obviously disconnected from the circuit, which makes it a natural response problem. Looking at this one, when that switch closes, that short is going to allow all of the 2 amps of current from the current source on the left to effectively, all of it's going to flow through the switch. None of it is going to be able to flow to the right using Kirchhoff's current law. Therefore, that 2 amp source is disconnected from affecting the behavior of the inductor on the right-hand side of the circuit. So it's also a natural response problem. So the short answer is, if sources are left in, treat it as a total response problem. If sources are taken out, it's a natural response problem. If you're not sure, treat it as a total response problem. All right, so let's go back to this web work set. Let's find something that looks difficult-ish. This is a natural response problem. Let's work this problem. So this is homework 14, problem 5. We have some voltage source, 10 volts. Four ohm resistor in series with a 30-volt voltage source. And then we have a switch up here that is opening at t is equal to 0. Here we have a 1 ohm resistor Then we have a 1/2 Henry inductance. This is our current IL of t, which I believe we're solving for in this thing. Let's also solve for the voltage drop, bless you, across this resistor as a function of time. So first, is this going to be a total response or a natural response problem? A total response problem, because the 10-volt source on the left-hand side is always connected. So this is a total response problem, okay? So our first step is going to be analyze the circuit at t is equal to 0 minus. Okay? So at t is equal to 0 minus, is my switch open or closed? Closed. So here's my 10-volt source. Here's my 4 ohm resistor over which I have my voltage VR at 0 minus. Here's my 30-volt source. Since my switch is closed, I'm just drawing a short circuit up here. Since we are at DC steady state, my inductor will look like a short circuit as well. Here's my inductor current at t is equal to 0 minus. How would I solve for either of these quantities? So let me answer. I heard several different things, all of which would work, and then I heard a question specifically: is VR 0? And the answer is no. So let me explain why VR can't be 0. If we were to do Kirchhoff's voltage law around this loop, we would see that VR minus 30 volts is equal to 0, which means VR has to be equal to negative 30 volts. Are we okay with that? Anybody got beef? Oh, sorry. You're right. Positive 30 because of the polarities there. So 30 with positive on the left plus 30, excuse me, 30 with positive on the left plus 30 with positive on the right are going to make 0. You're right there. I just messed up the sign. Thank you for that. I mean, I was testing you. That wasn't my mistake. Yeah. Yeah, testing you guys. But the process there of applying Kirchhoff's voltage law is correct. I'm just bad at negative signs, which I've been very upfront about this entire time. So no surprise there. All right, how do we find IL? Yeah. So what's my Ohm's law equation going to look like? You guys are taking a long time for something that I believe is 10 over 1. That's it. 10 volts over 1 ohms is 10 amps. Absolutely right. Walker. So let's pretend we were doing nodal analysis here. Okay. The bottommost node is ground. What's the voltage at this node? If I identify this node, this is all one node, right? Because there's that short circuit over the top. So if this point right here is at 10 volts, this point over here also has to be at 10 volts because it's all the same node. There is no voltage drop over the short circuit across the top, right? So I would have 10 volts minus ground divided by 1 ohm is my current flowing through that 1 ohm resistor, which is the current flowing through my inductor. Nope, it's just going to cause current to circulate in this little loop that I've already described with the blue line. So because there's a voltage drop across the 4 ohm resistor, there is absolutely current flowing through that 4 ohm resistor, but all of that current is going to circle back around in that loop to make Kirchhoff's current law equal to 0 at all of the nodes. Any other questions about our analysis here? All right. Now we're going to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, that switch is an open circuit, so I'm just not going to draw that top path at all because it's just an open circuit. So we would have 10 volts in series with a 4 ohm resistor over which there is a voltage VR at 0 plus. Here we have our 30 volt source. Here we have our 1 ohm resistor. What's our inductor going to look like? Current source. What direction is it going to have? Down. What magnitude is it going to have? 10 amps. Right? We know that IL at 0 plus must be equal to IL at 0 minus is 10 amps. So what's VR at 0 plus? $40 volts from Ohm's law, right? We know that there's 10 amps flowing around that single loop circuit. We have a 4 ohm resistor, current's flowing into the positive polarity terminal. So 10 amps times 4 ohms is, sorry, don't know what's going on there. $40 volts. Let me zoom back out because that's going to bother me. Well, apparently I'm zooming in the wrong direction. There we go. Sorry about that. Any questions, comments, or concerns about our analysis here? I use that loosely because we're just throwing Ohm's law at it. Let's scroll up and see, but I believe so, yes. So this is the first time we're actually going to have to do something here. We're going to have to analyze our circuit at t is equal to infinity now because there are sources left in, so we cannot just simply assume that our inductor current is going to decay to 0 in this case. Give me just a second to figure out why my laptop battery is about to die. This is plugged in. This is plugged in. Okay. Switch over here somehow got turned off. All right. So now we analyze our circuit at t is equal to infinity. So this is the first time we've had to analyze a circuit at t is equal to infinity. I want to remind you that anytime we are at t is equal to infinity, we are once again at DC steady state, which means all of our inductors are going to look like short circuits. All of our capacitors are going to look like open circuits. So this is literally just going to be the exact same thing as step number 1, except the switch is in the opposite state. Okay. So for us, that means we're going to have 10-volt source, a 4-ohm resistor, over which we'll have a voltage drop VR at infinity, our 30-volt source, our 1-ohm resistor, our inductor is now a short circuit again. Here's IL at infinity. How do we solve for VR and or IL? So you are assuming then that there is no voltage drop over the 1-ohm resistor, which I don't think is correct. Yeah, absolutely. So what Christina is suggesting, and I might be taking this one step further, we can see that we have 2 voltage sources that are in series, so we can combine them. Are the voltage sources of the same polarity or are they of opposite polarities? Same polarities. So I can get rid of this 30-volt voltage source here and just call this one a 40-volt source because 30 plus 10 is 40 volts. Using voltage division, VR of infinity would be 40 volts times 4 ohms over 1 ohm plus 4 ohms. So 40 times 0.8 is, if I'm not mistaken, 32 volts. What will IL at infinity be? So 32 volts divided by 4 ohms, or we could say 40 volts divided by 5 ohms. Either way, doesn't really matter. 8 amps. Any questions about our analysis here? Yes. We could have done KVL where we would have just said that the current IL is the current flowing around the loop. We would have found IL first and then use Ohm's law to find VR. But we did it effectively in a different order because we did it a different way. But you could have done KVL because that's a single loop circuit for sure. Yep. All right, so we know what the circuit was doing at t is equal to 0 minus. We know what the circuit was doing at t is equal to 0 plus. We know what the circuit is doing at t is equal to infinity. Now we need to calculate our time constant, okay? So step number 4 will be Determine tau during the transient condition. All right. So during the transient condition, our circuit looks like this. Here's our 10-volt source. Here's our 4-ohm resistor. Here's our 30-volt source. Here's our 1-ohm resistor. Here is our, if I'm remembering correctly, half Henry inductance. So we have an RL circuit. So what is tau? LEQ over REQ. Absolutely right. What is LEQ? Half a Henry. There's only one inductor, so that part is very easy. Okay. How do we find REQ? We take the inductor out, look in through the inductor terminals at a dead network, which means our 30-volt source needs to be shorted and our 10-volt source needs to be shorted. What do we see? 5 ohms. So it looks to me like we're going to have 0.1 seconds as our time constant. 0.5 divided by 5 is the same as 5 divided by 50 is 1/10. I believe I'm doing that mental math correctly. So 0.1 seconds. It may not be obvious that the units here are seconds, but remember that a Henry is a volt second per amp, and an ohm is a volt per amp. So the volts per amp cancels, and all we're left with is seconds in the numerator. It'll work the exact same way for the time constant for capacitance. The time constant is always measured in seconds because it's literally the amount of time it takes for the energy to dissipate down to 13.67% of its original value. Okay. I personally also like to find the inverse of tau, which in this case would be 10 per second. The reason why I like to find the inverse of tau is because in step number 5, plug stuff in, our generic formula let's see, y at 0 plus minus y at infinity e to the negative t over tau plus y at infinity. Well, if I know what 1 over tau is, that's what's multiplied by t. So there's our generic equation. So let's find out what IL of t is. So what value did IL have at t is equal to 0 minus? 10 amps. What value did IL have at 0 plus? What value did IL have at infinity? E to the negative, so what's the inverse of tau? 10 t. Y at infinity was 8 amps. And very obviously, we could just call this thing right here 2 amps if we wanted to. 10 minus 8 is 2 all day long. Now let's find VR. What was VR at 0 minus? 30 volts, right? What was VR at 0 plus? Then it was 40 volts. VR at infinity? 32. E to the negative 10t plus 32 volts for t greater than or equal to 0 plus. And this is very obviously just 8 volts if we wanted to simplify it as much as we possibly could. So, as far as I am concerned, I've taught you all that you need to know to be successful in analyzing any transient analysis problem you'll face in this class, or any first order transient analysis problem you will face ever. This is the process. I'm more than happy to work more example problems. I'm more than happy to let you guys just work on your in-class assignments, and I'll answer questions as necessary. Which route are we going? More examples. All right, so I brought a textbook for a reason. So let's work one with a capacitor. So let me just find one that is a first order circuit. With a capacitor. And I don't need a bunch of stuff with op amps. Okay. All right, so here is our circuit of interest. Let's say that we have a 16-volt source. Our resistor here is going to be 2 kilo ohms. Here we have a capacitor that is 25 microfarads. This will be our capacitor voltage, Vc of t. We'll have a 2 kilo ohm resistor right here and a switch above it. Let's have this switch closing at t is equal to 0. Let's put a resistor here. Let's make this 4 kilo ohms. And there is our circuit of interest. So, one thing that I want to point out about this particular circuit, this is still going to be a transient analysis problem because the circuit is undergoing a change, but the change doesn't have anything to do with the sources whatsoever. It's effectively, the change is what the resistance seen by the capacitor is going to change as that switch changes states, which is still going to cause some perturbation in the system that will give us a transient response. So once again, transient analysis is just what's going on while the system is in a state of change, okay? So what is our circuit going to look like at t is equal to 0 minus? So at t is equal to 0 minus, we have our 16-volt source, 2 kilo ohm resistor. And let's find this current IR of t as well. This is going to be Vc at 0 minus. Our switch is open at t is equal to 0 minus, so I'm not drawing that top open circuited path. So how could I find VC at 0 minus or IR at 0 minus for this circuit? Nodal's overkill. Mesh, there's only one mesh, so yeah. One of my Kevins, tell me what you would do. Okay, well then the other Kevin. Yeah. So you can do KVL around this loop to find IR for sure, although this is just a single voltage source connected to 3 resistors in series. So I would argue that you could probably just skip the KVL part and just throw it into Ohm's law with our level of current understanding to find IR. We could also use voltage division to find VC because VC is just the voltage drop of the 2 kilo ohm resistor in series with the 4 kilo ohm resistor. So a couple of different ways that we could do stuff here, none of which should involve setting up a system of equations, just as a heads up here. So if we did KVL around this loop, what we would find is that negative 16 volts plus 2 kilo ohms plus 2 kilo ohms plus 4 kilo ohms times IR at 0 minus is equal to 0, which means IR of 0 minus is 16 volts divided by 8 kilo ohms is 2 milliamps. And again, we could have gotten that same thing really just using Ohm's law if we had so chosen. Knowing that resistor current, how do we find VC at 0 minus? Kirchhoff's voltage law around this path tells us that VC at 0 minus will be equal to 2 kilo ohms plus 4 kilo ohms times IR at 0 minus. So 6 kilo ohms times 2 milliamps is 12 volts. Anybody have any questions, comments, or concerns about the analysis that we did there? Nobody's piping up, so I'll assume you're all good with it. So at t is equal to 0 plus, how is our circuit going to look different? So our switch is shorting out the rightmost 2 kilo ohm resistor. So I'm going to represent that by just no longer drawing the 2 kilo ohm resistor. I'm just going to replace it with a short circuit. So we're going to have our 16 volt source. Two kilo ohm resistor right here. I'm leaving this path down here blank for now because you guys are going to tell me what that's going to be in a moment. Here's my 4 kilo ohm resistor through which my current IR at 0 plus is flowing. What's my capacitor supposed to look like here? A voltage source, okay. Positive polarity terminal on top or bottom? Top, because VC was defined with positive polarity terminal on top. What is the value of this voltage source going to be? 12 volts. Okay. So just to really hammer this home, VC at 0 plus must be the same as VC at 0 minus is 12 volts. IR at 0 plus is going to be what? Exactly right. 12 volts divided by 4 kiloohms is 3 milliamps. Does anybody have any problem with the analysis that we did here? Okay, fairly straightforward. At t is equal to infinity, we're going to have the exact same circuit we had at t is equal to 0 plus, except now our capacitor is going to look like an open circuit. So how would we find either VC or IR for this case? Yep. So IR at infinity is 16 volts divided by 6 kiloohms. So that is 8/3 of a milliamp. VC at infinity. Well, you don't even have to do that. It's just the voltage drop over the 4 kiloohm resistor, right? So we could just use Ohm's law again. So 4 kiloohms times 8/3 of a milliamp. So let's see, 4 times 8 is 32. So 32/3 of a volt. How do we find tau? So during the transient condition, we have following circuit, 16 volt source, 2 kiloohm resistor, 25 microfarad, I believe, yeah. Four kiloohm resistor. Tau for an RC circuit is REQ times CEQ. What's CEQ? 25 microfarads. All right, to find REQ, we would take our capacitor out and look at a dead network. So we have 2 in parallel with 4. Right, so that's going to be 8/6 or 4/3 of a kilo. Throwing that into the calculator. Let's see. So 25 times 10 to the minus 6 times 4/3 times 10 to the 3. It's giving me some dumb syntax error, so let me do this manually. Yeah, it's ridiculous. Quite funny if it is. All right, so I get 1/30th of a second. So that's going to make the inverse of tau really easy to figure out. It's 30 per second. And now we are just plugging stuff into our generic equation. So VC at 0, VC of t. What was VC at 0 minus? So VC at 0 plus also was 12 volts. What was VC at infinity? E to the negative 30t plus 32 over 3 volts. So let's see, 36 over 3 minus 32 over 3. So this is going to look like 4/3 of a volt. For IR, what was IR at 0 minus? What was IR at 0 plus? IR at infinity. E to the minus 30t plus 8/3 of a milliamp for t greater than or equal to 0 plus. 9/3 minus 8/3, this looks like 1/3 of a milliamp. Do we need to do more of this? The process is literally the same thing, except that what's going on at infinity is no longer 0. Okay. All right. So you guys have about 40 minutes or so to work on your in-class assignment. If you have any questions about anything, I would be more than happy to answer it. So on Monday's class meeting, okay, I've covered all the material that I need to cover for this. So on Monday's class meeting, we are just going to work the in-class assignment together. It's the first problem you guys might see where there's more than one energy storage element because I have 2 inductors in parallel. Ooh, scary. But we're going to work that problem, and then we're going to do the lab, and that's it. We can, yeah, so that's it. So Monday should wrap up relatively quickly if the lab isn't wildly difficult by any stretch of the imagination. We can use the remainder of that class period for review-ish if you guys want to. I have no problem with that. Wednesday and Friday of next week, we will be covering op amps. Op amps is not on your upcoming test. That is the first material that will be on exam number 3. So as far as I am concerned, we have covered all the material that you will be tested on for exam number 2. So I hope to be getting some questions about the practice tests over the next couple of days because you guys should be working on them now for sure. Okay, enough ranting out of me.